Ready? I just want to make sure, can everyone hear me without the microphone? Yeah? All right. We tend to like to walk around as we talk, so the microphone is not very conducive to that. So today, we're going to talk to you about one of our favorite subjects in all the world, ZFS. And normally the subtitle for this is The Last Word in File Systems. But since we're going to tell you about some things that we've recently completed and what we're going to be working on over the next period of time, we thought we'd call it the next word of ZFS.
And we'd update the picture, but
we like them.
We like them, and it will be a lot of work.
Yeah, so what's in the pipeline with ZFS? Well, number one is we've introduced a lot of features over the past year, and now, of course, comes time to make it go fast. A lot of people have mentioned that they'd like to see performance of ZFS improved. You are not alone. We would like to see it improved as well. So that's going to be one of the key elements that we're going to be working on over the past year. And I should note that some of these that we say in the pipeline are actually done and put back into Open Solaris. The second example there being an example of that, which is user quotas. So for the longest time, ZFS has had the ability to specify on a per file system basis the maximum amount of space that file system is allowed to use out of the pool or a quota. For a lot of people, they say, yeah, that's interesting, doesn't solve my problem. I want to assign on a per user basis a quota. So we finally got around to doing that. Pool recovery, when something bad happens, how do you get back your pool without being an on-disk format modifying expert? So we're going to add some tools about that. We've had single and double parity RAID Z for quite some time. The same guy, Adam Leventhal, that did double parity RAID Z was nice enough to figure out how to do triple parity RAID Z, working on quadruple parity and beyond, just for those of you who like making really wide stripes and having a lot of extra disks there. Deduplication, of course, a very hot topic. We'll have plenty to say on that later. On-disk encryption, Darren Moffat is getting incrementally closer to that. BP rewrite, we'll talk about that more and how it relates to device removal. Shadow migration, or brain slug, as some of you might have heard it called, and other random things that we may think about talking about. All right.
So, we've got a whole bunch of topics on performance, but hybrid storage pools we'll get into in a little bit more detail. But I just want to give you a taste of a few other things that have happened, just in a sort of short summary. So the first is we have a new block allocator. So it might be surprising, but from the very beginning days of ZFS, we had an extremely simple, naive block allocator. The entire amount of code that we had dedicated to block allocation was about 80 lines of code. It was just ultra simple.
With a big black comment that was invisible to everyone but Jeff and myself saying, "Fix me later."
Right. And so eventually later came along, and it was not either me or Bill, but George Wilson who did that work for us. And the thing that was actually the motivation for it was, oddly enough, as simple as the algorithm was, it actually performs quite well when the pool is not yet reasonably full. As the pool starts to get full, and you get into this business of trying to find where can I get contiguous space so that you avoid having to do gang block allocations, then it starts to get more and more pathological, because things were sorted only by offset, not by size, and it took a while to find something of the size that you wanted. So what we have now is something that's sort of a hybrid between a best fit and a first fit. It does first fit while there's still lots of space available, and then as it starts to become harder to find contiguous space, it switches over to best fit and being size-based. It allows us to sort of have the nice balance between, you really want to be offset-based, so that you can keep things as contiguous as possible when it's not too full. But as it starts to get more full, you just got to find space reasonably quickly.
Yeah, and the thing that made this a little more difficult is on the on-disk structures, the space maps, we actually had to add more data to those, a little bit actually, to be able to handle the sorting by size so that we know out of all the space maps we can choose, which one is most likely to have the amount of contiguous free space we're looking for. So the next one up there is what we call raw scrub. So scrubbing, if you remember, is the process by which I run through all the pool and all of its metadata, reading all the copies of the blocks, making sure they all match their checksums and everything's in good shape. But the downside of that is, for example, say if I read a compressed block, what I would do is I'd read the block, checksum it, decompress it for no particular reason, and then throw the data away. And sort of a waste of time. So we've now added the option to have a raw scrub, where we just read the block, validate its checksum, repair it if necessary, and then don't bother uncompressing the data, just throw it away because we don't need it anymore. And this will especially be valuable when we get to on-disk encryption. Is because without this change, we'd have to decompress, decrypt, and everything the block that we're about to throw away, which huge waste of time.
And not only a waste of time, but also potentially a correctness problem in that you want your storage pool to be able to do things like hot spare in a disk drive, even if you don't have all the encryption keys available at the moment, right? So you don't want your data maintenance procedures to depend on availability of all the keys. Next up is parallel device open. That one is exactly what it sounds like. When we open devices, we do it all in parallel. It's an easy enough thing to do. We didn't do it before, though. We do now.
Yeah.
Zero copy I/O is sort of a familiar concept. That was actually something that was requested by the Luster folks because it was very important for them, but others will benefit as well.
And it actually implemented by them, so
yep.
That was very nice of them to help us out in that regard. Next is Scrub prefetch. So one of the things people have complained about with Scrub for a long time is that it is very slow at making progress. One of the reasons it's slow is because it doesn't utilize any of the prefetch code or any of the, well, I guess it does use some of the caching. But we've now added the ability for the Scrub code to go and prefetch a bunch of blocks, which will just increase the utilization of the storage pool when it's otherwise idle, to help get that scrub done a lot quicker. So repairs and resilvers and things like that won't take nearly as long. Native iSCSI, the Comstar project went back, what was it, last year sometime,
yeah.
Summerish. And for the longest time, they weren't able to fully integrate with ZFS. You know, we had to add some stuff, they had to add some stuff. So now we have Comstar going into ZFS and keeping some metadata for itself off to the side of one of our ZVols. So now we can implement much more high performance in-kernel native iSCSI.
Yeah. And then the next step on that is going to be taking it and getting rid of the ZVol component entirely and just having all the I/O path go directly through the DMU interfaces, because there's no reason to go through the block device layer at all.
Yep. The sync mode, this has been a sore point for me personally for a long time, which is whenever people do like NFS benchmarks, and it really has not much to do with ZFS, but like Solaris versus Linux, the default mode on Linux is that when an NFS request comes over the wire, you write it, you don't issue, you know, an fsync on the file. You just say, yeah, it'll get there eventually, even though the NFS protocol says, before I acknowledge to the client, has to be on disk. And the Linux guy's attitude was like, yeah, but it's all right most of the time, and it goes a lot faster if you don't actually wait for it to go to disk. Of course, our NFS team is not quite so laissez-faire with their, or laissez-faire with their attitude, and they're like, you know, the spec says you wait till it's on disk, we're waiting until it's on disk, sorry. And that is a sore spot for a lot of people that say, well, Solaris then is perceived as being hyper slow, it sucks, compared to Linux. So now what we do is we're going to offer a mode to where you can say honor synchronous semantics all day, every day. You can have one that's sort of in between, which is just keep things ordered on disk. So if you make modification A before modification B, they'll both eventually go to disk, and we'll always guarantee the order between them, which is 98% of what you wanted out of the synchronous mode in NFS anyway. And then lastly, the Linux mode, which is just, yeah, just push it to disk when you get a chance, tell everyone it's fine, and off you go. So it'll be a tunable property on how the ZIL behaves going forward in time.
And this last item, just-in-time decompression, is another fairly simple change. The idea here is if you're going to go off and do something like prefetch data, and the reason that you're doing prefetch is because you want to hide the latency of the I/O. But on the other hand, if you prefetch something and do all the work of decompressing it, you're potentially burning a bunch of CPU on something that ultimately won't be useful, if it turns out that you prefetched a block that in fact didn't get accessed. So the idea with just-in-time decompression is you prefetch stuff, but you don't do any of the computational work on it. And then as you discover that you truly do need the data, then you apply the computational transforms.